So my name is Boris. I'm an engineer at 8x8. I work on the Jitsi team. And many of you probably know this guy. So he couldn't be here this week, but he says hi, everyone. So this talk is going to be about Jitsi Videobridge, which is our SFU. A little bit about our product. What we have is an open source system for video conferencing. So we have a bunch of server components as well as clients, web clients, mobile clients, SDKs, and so on, that can provide you with a feature-rich meeting solution. So it's sort of different than other projects that we've heard about in that it's not giving you individual building blocks, but it's giving you a more complete, customizable but complete system. There's basically 3 ways to use Jitsi. The easiest one is to go on the meet.jit.si website and just start a conference. Share the link, and you can use it there. It's a free service that 8x8 runs. The other way, of course, since everything is open source, is to run the code yourself. Nowadays, we have Docker containers for everything, so it's pretty easy to get started. Just go to the Jitsi.org on GitHub, and you should be able to find your way around. Finally, we have the Jazz service, which is our hosted service that can be easily embedded. So we solve some of the problems for you, such as high availability, scaling, geolocation, and so on. A little bit of history. Jitsi has actually been around for quite a while, as well as the SFU. What you see here is the Jitsi desktop client that is now not in use anymore. But this is the Jitsi desktop client using Jitsi Videobridge to host the conference. So this was FOSDEM 2013. And it was one of the earliest versions of Jitsi Videobridge. The code used to be part of the client itself, but then we moved it out. So for a little bit of context, I'm pretty sure this was a few months before all the Codec wars at WebRTC started. So this was running without WebRTC. We had no idea that it's an SFU. I think it's just mixing audio at the time. But that's how it started, and over the years it's evolved a lot, of course, and it's been completely rewritten since then. But it's a mature project that we've been using for a long time. So around the end of 2013 is when we added support for WebRTC. I think DTLS was the main thing that was missing. And then we started playing with Philip Hanke's JavaScript client, and that evolved into Jitsi Meet. A little bit about the architecture. When 2 endpoints want to join a conference, they go and talk to a signaling server, and that's separate from the SFU. So that signaling server chooses an SFU for them, and they establish WebRTC sessions with it. So the job of the SFU is just to route packets, not do like heavy signaling. And if we want to do extra things like stream the conference to RTMP or things like that, or connect to the PSTN or SIP, or do transcription, any of these things, we add a regular endpoint, connect over ICE and so on. So the SFU just does SFU stuff. Well, what is SFU stuff? SFU stands for Selective Forwarding Unit. It's, at least in the context of WebRTC, it's a middle box that doesn't decode things and just forwards packets selectively. Selectively, we'll go over what I mean by that, but what are the more interesting things that the SFU does, and what I'll talk about today is a little bit about codec support, a little bit about bandwidth allocation, which is about how do we decide what to send to a certain endpoint given constraints in bandwidth. And then cascading SFUs, which is something that I love talking about because it's a cool project. A little bit about codecs in WebRTC. When I made this slide, I thought I was just going to say, hey, audio is easy. But I thought about it, and it's like, I don't know if it's easy or not. But we have Opus, and that's been an amazing technology, and we take it for granted. But it's really interesting to see how it's used in so many cases. We have Hollywood productions using 7.1. We have super constrained bandwidth with lots of packet loss, but it just works. So as far as we're concerned, audio is easy and we take it for granted. Video is a bit more complicated. Nowadays, browsers have these three codecs mainly, VP8, VP9, and AV1. And without assuming things about where the code is going to run, what devices, and so on, we cannot say that one is the best solution. VP9 and AV1 offer a better trade-off between quality and bitrate, but that comes at an extra complexity cost. So if we have a mobile device that is getting overloaded, say, another Android device, we might want to switch away from AV1 and downgrade to VP8 to save some resources. And in fact, that's what our client does. So most of the codec support is on the client side. That's where the decisions of which one to actually use are made. But our SFU needs to be able to use these codecs and switch between them dynamically. So if we just have a regular video stream with no special scalability built into it, the SFU doesn't really have a good choice. It can either forward the stream or not forward the stream, and that's what you get. So the way to go around this is to use things like simulcast and scalable video coding. Simulcast just means that we are independently encoding a bunch of streams, or a stream is independently encoded at different resolutions, and the SFU is able to choose which one to send and switch between them at keyframe boundaries. Scaling video coding is a technique that allows us subsets of packets or subsets of frames to form layers with different quality, whether that's resolution, perceptual quality, or frame rate. And actually, when we use simulcast with VP8, for example, we also have temporal scalability. So each of these streams can be broken down into 30, 15, and 7.5 FPS, basically. So when the SFU receives one of these scalable streams, it can select any of a number of layers to forward to any particular receiver. And this is where layer selection comes in. By layer selection, I mean that given a particular receiver, we have to select from each of the available sources 0 or more layers to forward. And we are subject to some constraints. We have an estimation of the available bandwidth, and we have some preferences coming from the receiver. So we also refer to this as bandwidth allocation, because one way to think about it is you have X amount of bandwidth. How are you going to allocate it between the different sources? The preferences from the receiver we describe with a structure like this. So we have last n. This just means the maximum number of streams that the receiver wishes to receive. We have a list of on-stage sources that we'll talk about later. And then we have some constraints in terms of resolution for each endpoint. So Depending on what the user interface looks like, clients can use different constraints to achieve what they need. So for example, if your interface looks like this, so you have 6 tiles, you might want to say, I don't want more than 6 streams, and I don't want more than 360 for any of it. And the question we're asking is, how are we going to select the different layers as bandwidth changes? So if we have no bandwidth, we're not sending anything. If we have a little bit of bandwidth, we're going to use speaker detection to figure out which source is the most relevant. We're going to start sending you that, and we're going to send, if we only have bandwidth for one layer, we're going to send the lowest layer, so a 180p stream probably. As we get more and more bandwidth, we're including more and more base layers. So we're trying to fill all the tiles before we upgrade any of them to a higher resolution. So once we fill this, if we have more bandwidth, we'll upgrade this first one to 360, and so on. So the goal of this is to provide the user with relevant video, and to be consistent. We want to avoid switching too often because that lowers the perceptual quality. Now, this is all driven by speaker order. So if I change the example and I have 5 streams, we're going to discard the last one in the speaker order. And then if that one starts speaking, we're going to swap. So it should be pretty intuitive. If, on the other hand, your interface looks like this, so we have one big stream and then 3 small ones, and then I've tried to include some that are out of your window, but you could scroll to them. You might want to choose something like this for constraints, where you've constrained these small ones to 180, the larger one to something more, and you've also put the larger one on stage, which is going to change the behavior here, and we're going to allocate greedily until a certain point before we start including little ones. So we're going to allocate up to 360, then we're going to do 180 for the ones down low, and then we'll update to the full resolution, assuming that's 720. The other things that we use these constraints for is restricting the send side streams. So if endpoint B, no one is requesting more than 360p from it, we're going to tell it to go and scale down so that we're not wasting resources. And it can go all the way down to 0. And we can also use this to adapt to load. So if we detect we're getting overloaded on the client side, we can drop down to a single stream, as well as switch to like VP8, things like that. So that's how our bandwidth allocation works in a few words. On to cascading SFUs. First, by cascading, I mean we're going to interconnect 2 of them or more. And we're going to have different endpoints connecting to either one joining the same conference. Now, why would we want to do that? One reason is to minimize latency. If we have a situation like this where we have some participants in the US, well, you can barely see that, and some participants in Europe, and we have a single server, the link from Krakow to my hometown of Sofia goes through the US, which is less than ideal. So if we introduce a cascade there, we can lower the latency to the next hop, which is useful because, well, presumably it's a better connection, and then retransmission happen faster. There are some downsides, and it can have a negative impact if we do it too finely. So if we have servers in London and Frankfurt, as is the case, and we have endpoints that are equally close to each, we might be adding an extra hop there that is not helping. We actually did some research on this by measuring the end-to-end delay between each pair of endpoint in conferences on our service. And the basic finding was that if we have different regions in Europe or in the US, it doesn't pay to do cascading for that reason. But if we keep the regions broad, so we have the whole US as one region, whole of Europe as one region, and so on, then we do get positive effects. Another reason why you might want to do cascading is being more efficient in the way you balance load between multiple SFUs. So the problem we have is we don't know the conference size in advance. So we allocate conferences to different servers, and suddenly a conference grows to 100 participants, and that takes a lot of resources, and that server is getting overloaded. And if we have the option of cascading, we can just threshold it 80%, I think we use, and that's when we reach a load of 80%, we start splitting those conferences and start using more than one. There's a little bit of overhead there, but overall, we avoid spikes in load. And the third reason is to just scale to larger conferences. So no matter how performant the SFU is and how big the hardware is, you're likely going to reach limits at some point. And at that point, it pays to be able to just spin up another one, make larger conferences. The way we do that is we interconnect the SFUs in a full mesh. So any packet received by an SFU from an endpoint gets forwarded to all other SFUs. And finally, this is a more recent project that we've worked on this year and the last year. And it's a pretty cool project where we want to scale to something like 10,000 receive-only endpoints. So we want to have events where we have participants that are in the conference, they have the native experience, they can switch between different streams and so on. But we want to avoid the 2-second delay or so of technologies for live streaming. And we also want to allow any of them seamlessly to actually join the conference and ask questions. So one use case for that is events, private events with Q&A in the end. So we want to provide that sort of experience to users. And the way we did this is by adding more meshes. So we're doing a multi-level scheme where the receive-only endpoints have their own second-tier SFUs that they connect to. And then the green connection there is one-way. So we know that this is easier to manage. With this, we have synthetic tests with up to 10,000. But mainly we're using it for smaller events, as I said, to allow a cleaner interface for one thing, and then people to switch seamlessly and join the conference with approval. So the way it works is, if you're a receive-only endpoint, you cannot participate, but you have a button that can move you, and we're going to switch you to a different SFU, and then you're in the conference and you can actually participate. So that's what we use cascading for. That's pretty much it. I think I'm a minute early, actually. Any questions?
Hey, really fantastic, and it's nice how much you're sharing about how you're solving certain problems. Are you using a third-party tooling to do your 10,000 test, or how do you do the synthetic test?
Third-party tooling, it's a Selenium grid. So it's like 200 machines running our own client, like with things removed, so it runs it faster. So I think we can run about 50 to 100 per machine, something like that.
Okay, but it's,
They're actual
it's your own
headless
custom
browsers.
code for the load testing.
Yeah, it just runs on top of Selenium grid.
So, okay, cool. Thank you.
There are several more questions.
Test, 1, 2. Okay, so first of all, thank you for the presentation and especially for open sourcing such a powerful tool. So my question is, what strategies do you use for estimating bandwidth on the client side? And which strategies did you try and which ones didn't succeed? So
That's a good question. So we're pretty much following what WebRTC does. So we have our own port of the WebRTC, libWebRTC bandwidth estimation code. I don't understand the details too well, but the idea is you monitor jitter and you monitor packet loss, and you drop your estimate if you see packet loss and jitter. For the SFU, there's a bit of a problem because it's hard for bandwidth estimation to ramp up unless you're sending data. So to deal with that, we have a probing. So we're sending a little bit of garbage if we need to, in terms of RTP padding. Thank you.
Hello. How do you choose which layers to select? Do you do it all server side, or do you do it client side and server side?
Yeah, so it's a combination. Client side.
Do you end up looking at WebRTC stats client side as well and actively saying, something bad's happening, I want to do this?
No.
Or are those decisions all server side?
The latest versions of the bandwidth estimation run stand side. So on the SFU, we have locally the estimate of the available bandwidth. So that's where that comes from, and then the constraints come from the client.
Thank you. To choose the layer side, do you also take into consideration the CPU constraints on the receive side or memory constraints, which might, bandwidth might be fantastic, but if you're running on a low-end machine,
right,
you will still receive a poor video quality. How do you tackle that?
We use this option, the last N. So we limit the number of streams. So if a receiver detects that it's getting overloaded, it's going to just request less streams.
Do you use compute pressure API for that?
Yes. Unfortunately, I don't know the details. But I know that we do this on mobile for sure. Not quite sure if it's enabled on web yet. The question over there.
I think there is one question over here and some more questions.
I have a question regarding this scalable video codec. Are you sending video in this format directly to the browser or native smartphone application into decoding there, or you do transcoding in your service and send just some one-layer version there?
With AV1, it almost feels like we're doing transcoding because of the format of the RTP header extensions, but no, there's no transcoding. We're just forwarding packets.
Okay, thank you.
Okay, there are two more questions over there. Oh, the one behind you. Yeah.
Hey, you mentioned that you are sending some garbage on the SFU to probing. I'm just curiously, have you considered to send, for example, FEC packets instead of garbage?
What packet, sorry?
FFAQ packets.
Oh, right. Yes. I'm struggling to remember what exactly we did. At some point, we were just using RTX to send duplicates. So that way, they're just going to be discarded if they're not needed, but it's not actual garbage. So if we cause some packet loss, where it can probably
just
be
because
Yeah.
I think the RTP FAQ in this latest form, what they did is actually considering that you can choose the interval how much dynamically. So you can basically dynamically say that, okay, I want to 10% garbage, 15% garbage, and so on and so forth. So
Okay, I didn't know that. That's pretty cool.
Yeah.
We haven't touched that in a few years.
yeah.
And I'm so glad I have a hat. I don't know how everyone else does it without one.
Yeah, thanks for the talk. As far as I'm concerned, Jitsi uses Java under the hood.
Yeah, on the
do
back
you-
end, it's mostly Java and nowadays Kotlin.
Okay. Do you have any problems with Java Virtual Machine, in particular with the garbage collection stuff? And do you do everything in Java Virtual Machine, or do you delegate to some low-level stuff?
A really good question. We only delegate SRTP decryption to OpenSSL because it's much faster. As far as memory management, it is a bit of a problem on the SFU where we're constantly cycling packets. So we actually use a memory pool in Java heap space. So we have a big chunk there and we reuse them. It's a bit of overhead in terms of we have to keep track of memory. But when we did it 6 years ago, experiments showed that it had better performance. It's on my list when I have some extra time to go and test the newer GC algorithms in the newer versions of Java and to actually see if it still makes sense, because at the time we were testing with up to G1. So that's something cool to test more.
Okay, so does it exclude the scenario when garbage collector runs and stops the whole SFU for a while because of garbage collection, or does it still happen but it's neglectable?
That's what we optimized for. So with the memory pool, we had shorter pauses overall.
Okay. Do you know how long are those pauses?
Not off the top of my head, I can check, but I'm pretty sure it's under 100 milliseconds.
Okay, thanks a
Still
lot. That was very
can be
helpful.
significant. Mm.
Let me check if there are any questions from the chat, because yes, we are streaming today and there are people watching us, but no, and unless there are any further questions, let's... Oh, there is one more question. Amazing.
Hey, is Jitsi suitable for big, larger meetings, for example, 100 publisher audio and video?
Yeah.
Okay.
On the public service, I think the limit is 500 right now.
Okay, so the next question is, do you have any strategy to reduce CPU and memory consumption on the client side when it comes, for example, to, because video is not a problem because there is some kind of pagination. But for example, when we use SFU and audio, there is a lot of connections. So
That's actually down my slides, the parts that didn't make it to the in time. For audio, we don't forward everything. We strip the silence and we only forward the top 3 speakers as of like in a very short window. And that's based on Chromium only mixing the top 3. That was a few years ago, and we knew that it was working well enough that we could drop everything else. I don't know if they still do that, but we still drop everything else.
okay, great. Because like maybe 2 years ago when we tried Jitsi, we have like we came across some problems with over 30 participants talking simultaneously. So
Okay.
this is kind of resolved, I suppose. Yeah.
Yeah, I don't remember when we introduced it. I'm pretty sure it's been there for a couple of years at least.
Ah, okay.
Scanning the audience for any further questions, but no. Thank you very much, Boris.
Thank you.